Okay, welcome everyone. We have a visitor today. It's Professor Raymond. So it's part of my evaluation process to make sure you get a very good quality education. So, and there's one more evaluator coming next Monday. So I get graded too. Does anybody have any questions about anything before we start? So we will have a problem session after class today, an Astro Lab, and we'll go over some more problems on balancing redox equations. So if you want to come to that, I have some stuff prepared. Okay, so where we're at is we're in electrochemistry, and today not so much, but next class we'll talk about how equilibrium and electrochemistry are related. But now we're going to start with just plain old electrochemistry. And right here is drawn, here's a figure showing a galvanic cell or a voltaic cell. So galvanic cell, voltaic cell. So something to note, this is the most classic battery you can have. So you have two dissimilar pieces of metal. So in this case, zinc and copper. So two different pieces of metal, and they're both in solutions. And in between them, this is a salt bridge. So let's talk about what's going on here. There is an anode and a cathode. So the anode is the source of negative charge. So if you have a hard time remembering which one's negative, anode, remember anion. The anion is the negative charge. Anode, anion. Cathode is a source of positive charge. Think of the T, kind of like cation, think of the T as a plus sign. That's the plus sign. And what happens in a battery as you connect it, the anode corrodes. I always remember it that way. I think anode corrodes. The anode corrodes and the cathode grows. So let me zoom this back a little bit. So if you look at what's happening with the zinc zinc metal, so the metallic atoms here, they're giving up electrons. Electrons leave, and then zinc ions go into solution. So over time, this little sliver of zinc will corrode down. And then the electrons, when they leave the zinc, they will travel along the wire, and they'll go over to the cathode. And along the cathode, you have the cations here, in this case copper. The copper cations are receiving electrons, so in this case, copper plus 2 receives 2 electrons and then forms copper metal. So copper metal then grows on the cathode. And as this is going, as electrons are transferring, you can do work. So as electrons are moving, you can do work. And if you were to measure the potential for this, and this would be 1.1 volts. So I'll go over what volts are in a second. But so I'm sure you know when you put a battery together, you can then run your car, like your little toy car or flashlight or something. You can do some sort of work with the electrons as it's moving. And how much energy that the electrons emit, that is known as the electromotive force, or the EMF. And I think I've mentioned this before. You think that when you connect wires together, electrons are moving really, really fast. They're not. They move extremely slowly, on the order of 10 to the minus 5 meters a second. So really, really slowly. What does move very quickly is the electromotive force, which moves via photons, which means it moves at the speed of light. So the force moves at the speed of light. I like how Ben Hameen has his Star Wars short. So yeah, the force. So the force moves at the speed of light, but the electrons themselves are moving very slowly. And so this is a standard cell, which means then that the concentration of the zinc ions here is 1 molar. The concentration of the copper ions here is 1 molar. And this is also at 25 degrees Celsius. So later on we'll talk about non-standard conditions, but right now we're talking about standard. Standard conditions are 1 molar and 25 degrees Celsius. So last thing here is a salt bridge. So if you take the salt bridge out, the battery will stop working. What the salt bridge does, so let's talk about what the battery's doing. Electrons are flowing from here to here. So let's say there was no salt bridge. That means that that negative charge would move here. This end would become negative, and this end would become positive. That would never happen in real life. That's a breaking of entropy. So when you have a salt bridge here, then negative ions flow towards the anode, and positive ions flow towards the cathode. And that will allow electricity to go. So that means that if you want to turn a battery off, one of the ways you can do it is removing the salt bridge. And that's important for corrosion. Later on, we're talking about corrosion. Corrosion is an electrochemical process. So if you want to keep things from, how do you keep iron from rusting? One of the things you can make sure is it never gets wet. If it never gets wet, then there's no way a salt bridge can transport ions. And then it's only when, if you notice that, when iron gets wet, oh man, it starts to rust fast. Why is that? Because then you've created a salt bridge. So, okay. So the other thing with the standard cell potentials, it doesn't matter how much stuff you have. So the electromotive force, it's an intrinsic property, meaning it's like density, right? So it doesn't matter how much stuff you have, that doesn't change. So it doesn't matter if you have an atom of zinc and an atom of copper, the potential between them is 1.1 volts. So let's say that I go out in the courtyard there and I get 2 of those stand-up pools. Have you seen like the commercials for those stand-up pools, like swimming pools? And then I get let's say I get a car-sized hunk of zinc and a car-sized hunk of copper, and I put those in each of those in one of those respective pools, and then I fill up each pool, one pool, the one with zinc with 1 molar zinc ion, and then the other one 1 molar copper ion. And let's say I make a big salt bridge and I connect the two, and then I have a wire and I attach a wire to the zinc and then a wire to the copper, and then I bring the wires together and I have my voltmeter and I'm sitting there. I'm like, what's going to happen when I have this huge hunk of zinc and copper? If I touch the voltmeter, it would read 1.1 volts. So it doesn't matter how much I have, the electromotive force for all these things is exactly the same. So, and we'll go over the tables later. And we're going to use E for this. E, I know it's confusing in some ways because in thermodynamics you learned E also means internal energy. In electrochemistry, thermodynamics and electrochemistry were developed independently of each other. And they picked some terms, and there is some crossover. But for E in electrochemistry means the electric potential. And the E0, this is the standard cell potential, is the potential for the anode plus the potential for the cathode. So what's the potential? The potential is voltage. So this is not in this class, but have you seen circuit diagrams like this before? So this is an example of a circuit diagram. This symbol here with the long side and the short side, this is a battery. Okay? So the long side is the positive charge, and the short side is the negative. This squiggly line here, this is known as a resistor. What is a resistor? Is something that resists the flow of electrons. The flow, I should say, current. So let's back up and talk about circuits. So currents, your current is your amperage. So amps, the number of amps you have, amperage. An amp, 1 amp means 1 coulomb of charge per second. And so a coulomb, so the charge of an electron is 1.6 times 10 to the minus 19 coulombs. And also Faraday's constant, 96,500 coulombs per mole of electron. So electron is the charge we use, but So current is how much charge is flowing through a wire. Of course, unless it's a superconductor, all wires have resistance. It's from the friction. It's the electrons rub against each other, creates friction. Resistors tend to heat up. Well, any time you have something that heats up, it's because of the friction of the electrons. And so then this symbol here, this is known as a capacitor. So a battery works, it's kind of like a well, like there's always water coming from a well. A capacitor, maybe a better way to think of it is think of a battery as like a car factory, like a Nissan plant or like a Ford plant. Think of a capacitor like a parking lot. So instead of electrons, we're talking about cars. Capacitor is a place to store charge, but it gets emitted very quickly. So think of it like a parking lot, whereas the battery is producing charge at a slow but steady rate. Capacitor can give you a really quick jolt. And then this squiggly line, this is an inductor. This is when the old way to do an inductor, you take something like a plastic tube and you just put a wire around it like this. So what does an inductor do? There can be signals that go back and forth. The inductor can slow some of that down, some of the noise within the circuit. If you see this line attached to 3 bars, that means ground. That's a grounded circuit. Not all circuits have to be grounded. And some other terms. So a volt. So the term volt means joules per coulomb. So joules is energy per charge. So amperage is the current, it's coulombs per second. So instead of electricity, think of water. So as water is flowing in a stream or a river, your current is how much water is flowing. Okay, that's the current, that's the amperage. How many electrons, how much water is flowing. The voltage is how much energy the water has, or how much energy each electron has. So the joules per coulomb is the potential, the voltage. So and maybe you've heard things like as far as like it's not the voltage that kills you, it's the amperage. Not necessarily true, but you can get hit with some really high voltage, but you can live to tell a tale. I've been hit with 1,000 volts. It didn't feel very good, but it was milliamps. So I got when I was in grad school, I was working on a machine, and one of the postdocs left the machine on. Well, at least part of it. It was an electron gun. It had a charge across the plate of 1,000 volts, and I was taking apart the machine, and my metal wrench touched the lead for that, and so I got 1,000 volts going through, and I guess I could have died because I remember it felt like someone punched me in my chest. And they told me later that's because my heart probably seized up. But I didn't defibrillate, so I live to tell a tale. But it doesn't feel good, by the way. You don't want to. You probably don't want to do that. But something like a bolt of lightning, you can have 1,000,000 volts and thousands or tens of thousands of amps. The circuits on the wall here, like right here, it's typically 10 to 15 amps and 110 volts. Depends on the circuit. And also, if you're wondering how that goes to our plugs, so the little one is the positive line. The bigger one, usually you've seen the plugs. I know I'm kind of making it larger than it should be, but the tiny one is called the hot wire. It's also the one that's painted black. The white wire is known as the neutral, and then the kind of round one, that's the ground. So I don't have my Mac plugged in, but the Mac actually, the power cable is not grounded. So another one is your car. Your car has no ground. So the positive terminal in your battery, that's the positive. It's also the hot wire, and the metal frame of the car itself is the neutral. So you need to have for the minimum for a circuit, you have to have a positive and a negative. The negative also is sometimes called the neutral. And many things that we have are also not grounded. Many light rail trains, like they're building the heart in Oahu right now. But like many of the subways system, the light rails, they have a positive wire. Usually it's a little more shielded, but the train track or one of the train rails can be the negative. So that's one of the things I don't touch it because it could be electrified. So did I mention this is green as well? Okay, I don't know if I said that. So the black wire, the white wire, and the green wire, and at least if you take apart wires here in the United States. What the ground does is so electricity travels by the path of least resistance. We humans, we are resistors. We're not conductors, we're resistors. We have a pretty big resistance on the order of mega ohms. So an ohm is the symbol of resistance. So we don't conduct electricity very well. Let's say you get shocked and you're part of the circuit. If there's a ground, the current will go towards the ground, typically more than it would be the human. So it's a safety precaution. So we're not going to talk about that too much, though. And one thing to note about this circuit, and I've drawn it this way, that the current goes from positive to negative. Okay, that is not how electricity travels. Like what actually is traveling are the negative charge. So really, all the circuit diagrams, everything you see is drawn backwards. And we have to thank for that Benjamin Franklin, founding father. What happened is that he didn't know if the positive or negative traveled, so he guessed, and he picked positive. And he guessed wrong. We know it's a negative. Have we changed our circuit diagrams and our equations? Of course not. We stick with it because we even know when we're wrong, we still stick it. Part of human nature, I suppose. There's other instances that we haven't known and we've guessed right. So sugars, at least here for biological things on Earth, are right-handed. So you'll learn. We haven't talked too much about chirality. You might have talked about 161. If you go into organic chemistry, you can learn about chirality. Certain molecules are chiral, which means there's a right hand and a left hand. They're not the same, but they're mirror images. Biomolecules, many biomolecules are like that. So glucose is also known as dextrose. So for dextrorotary, right-handed, we didn't know if it was right-handed or left-handed, so we guessed right-handed, and then we related everything after that, and we guessed right. So, but current flow, we guessed, and we guessed wrong, but we've stuck with our wrong choice. I don't blame Ben Franklin, though, for picking positive, because if you've ever worked on your car or worked on things, the positive terminal is the one that sparks. So if you want to know which one is more dangerous, it's the positive terminal. So, I mean, if I had no knowledge of chemistry and I said, which way is the current going, I would guess positive too. So, it's not a big surprise. Oh, and more equations, not for this class, but so you see power. The power in a circuit is the voltage times the current, voltage times the amperage. And voltage is joules per coulomb, and an amperage is coulombs per second. So then power, voltage times amperage, is joules per second. A joule per second is a watt. So that's the power of a watt. So like when you hear about like my vacuum cleaner is so many horsepower or so many watts, that's the power. That's how much energy can be expelled per unit time. So to give an example of that, imagine a Corvette or like a Honda Civic. Okay, so what's the difference between a Corvette and a Honda Civic? They weigh about the same, right? And that means when they're going 55 miles an hour, they have the same kinetic energy, the same momentum, right? So if the cars weigh the same and they're going the same speed, they have the same energy, the same momentum. What's the difference between a Corvette and a Honda Civic? A Corvette can get you there a lot faster, has more power. So the engine is more powerful. So that's where power is with time. Okay, how are we doing so far? Any questions? All right, so I talked about the standard cell, and the standard cell, what we had there was zinc and copper. The standard cell is the potential for oxidation and the potential for reduction. And, well, in this case, standard, all standard. And also, we can relate that the standard potential for oxidation is opposite the standard potential for reduction. So what we've done is that we have tables here. So this is the standard electrode potentials, and 25 degrees, that's the standard temperature. So we have a whole chart here, and this is a smaller chart. There's bigger charts if you want. These are, and this will be given to you. You don't have to memorize this, okay? This is not something to memorize. The only one that I only have one of these memorized. It's hydrogen. That's 0. That's the one that it's related to. So that's the, if you wonder which one do I memorize? I memorize the base. So how these have worked, we've gone and done the standard cells, and we've connected them up to hydrogen for acid. Two acids plus 2 electrons makes hydrogen gas, and then we've measured the potential for each one, all at 25 degrees and 1 molar, and that's the standard cell potential. And we have here, then, so here at the top, we have the strongest oxidizing agent, and the strongest oxidizing agent is fluorine. So this is the strongest oxidizing agent. And down here at the bottom, we have the weakest oxidizing agent, also known as the strongest reducing agent, and that's lithium metal. So the strongest, for a single cell, the best battery you can have is about 6 volts. So if you wonder, well, a car battery is 12 volts. So how do you have a 12-volt car battery? And electric eels, they have like thousands of volts. How does an electric eel, how do they do that? So if you put batteries in series, so if you have a battery connected to a battery, the potentials add. That's known as by series. So a car battery is actually 6 2-volt cells connected in series. And electric eel, they have, I mean, similar to our nerve cells, they have channels, ion channels connected in series, and they use that to stun their prey. But the cells are all in series. So you can have things in parallel or things in series, but series is how you get the higher voltage on our battery. So you get 12 volts or 6-volt batteries, kind of things. No one really uses a fluorine lithium cell. We use lithium. Lithium is often used for batteries for 2 reasons. It's really good reducing agent, and secondly, it's light. Lithium is a very light element. Okay, so I'll get to these charts later, but let's use this for an example. So calculating the standard electric potential for using half reactions. So this reaction here, aluminum plus nitrate plus 4 acids makes aluminum plus 3, nitrogen monoxide gas, and 2 waters. So if you look at the chart, so I've written it down here, but let's go to the charts. Let's look for aluminum. Where is aluminum? Okay, aluminum's right here. So aluminum, the potential for aluminum is minus 1.66. That's the reduction potential for aluminum. And then nitrate. Okay, where's nitrate plus 4? So that's the reduction potential for nitrate is plus 0.96 volts. Okay, so now the E0 cell, so remember this, the E0 cell is oxidation plus reduction. And these are, the chart here is reduction potentials. So we have to figure out which species is being oxidized and which species is being reduced. So remember oxidation. Oxidation means loss of electrons. Reduction means gain of electrons. Aluminum goes from aluminum metal with all its electrons to aluminum plus 3. So aluminum is giving up 3 electrons. Aluminum is being oxidized. Nitrogen here is gaining 3 electrons to become nitrogen monoxide. This is being reduced. So when we write out this equation here, we keep it, this is the reduction potential. But the oxidation potential, so if you see here for aluminum, this is the reduction potential, aluminum ion plus 3 electrons. It's going the other way around. Aluminum is being oxidized. That's why it's plus 1.66, not minus 0.166, because this is the oxidation potential. And the charts, though, the charts are all reduction potential, so it's this direction. So since we're going this way, we have to flip the sign. And then you just add these together. So then that's just 1.66 plus 9.96. So this cell here, the standard potential for this reaction is 2 point, again, I guess I covered up my decimal point, is 2.62 volts. So it's just the oxidation plus reduction. So you have to make sure, pay attention to the equation and see which way the electrons are flowing. Okay, before I get to the next one, I guess I might be showing my youth here. Does anybody watch like professional wrestling? I mean, I know it's all acting, but do you ever watch like, no, you haven't. Oh man, you ever heard of Hulk Hogan or yeah, Ultimate Warrior, Macho Man? Yeah. Okay, good. Good. We have some. I'm not too old then.
Oh, he's still famous.
Yeah. So whenever I looked at these, I always and of course in the professional wrestling, whoever is going to win, they already knew that. I mean, they're acting, right? No one beats Hulk Hogan. I mean, even Andre the Giant lost to him, right? So that's think of Hulk Hogan. He's like fluorine, right? And the strongest you can get. And I always pictured so in the ring we have iron and magnesium. Are you ready to rumble? And it's and we're gonna fight. And then you say, what's gonna happen? And we have a cheat sheet though. We have the cell potentials. So the question is, will iron react with magnesium ion to form iron ion and magnesium metal? Okay, so to me in the chart, I always look to see if which one was above the other. So what has to happen is, let's see here. Let's back up. The equation-ness of this is the Gibbs free energy. The Gibbs free energy is minus N. N is the number of moles of electrons transferred. F, Faraday's constant, 96,500. And then the E0 cell, the standard cell potential. So remember, if delta G is negative, it's spontaneous. Positive is not spontaneous, which means if E0 cell is positive, this is negative, then it's going to happen. So if E0 cell is positive, it's going to happen. E0 cell is negative, it's not going to happen. And so, which means, let's look at iron and magnesium. So we have, let me change colors here. So it's iron plus 2. Iron plus 2 is here, and magnesium is down there. So magnesium reducing. So this is going to be about minus 2.4. And iron going oxidizing is plus 0.45. So this is plus 0.5. So since iron is above magnesium, so are you ready to rumble? We have iron metal. Iron metal is above magnesium. Therefore, he's going to win the fight. Iron's going to win the fight. This is, I don't know, Macho Man versus The Undertaker. Macho Man wins. Right? So, nope. He doesn't get pinned like that. So then let's look about iron and lead, though. So iron's there. Where's lead? lead is here. Which one is which? So lead is above iron though. So what is iron doing? Iron is being oxidized, and lead is being iron is being oxidized and lead is being reduced. Okay, in this case though, the lead is above iron, so the iron going, so it's going the other way. So iron solid is going to iron plus 2. That's plus 0.45 volts. Lead going to the other way around. That is, wait a second. Sorry, let me see it again. So I'm sorry, iron is being oxidized and lead is being reduced. So iron is going the other way. It's plus 0.45. Lead's being reduced, minus 0.13. So since lead is above iron, lead actually is the stronger species, and then this does happen. Does that logic make sense, or is that okay? But I mean, you can always come back to the numbers. The numbers will always work. And it's positive E0 cell. So A is no, B is yes. Okay. Now going on. Metals dissolving in acid. Which metal dissolves in nitric acid but not hydrochloric acid? So let's go back to the chart here. It's getting busy. I'm going to erase some of this. So here are our metals. We have iron. I'll write iron there. We have, it's silver. Silver. And then we have gold. Gold is up here. Okay. And here's, I'll put there for the acid. So remember what's above what. So acid is above iron. So if you put iron into any acid, it will corrode. Okay, so all these metals, all of these metals, if you dump them into acid, they will corrode. Iron, lead, tin, nickel, cadmium, iron again, chromium, zinc, manganese, aluminum, magnesium, sodium, calcium, barium, potassium, lithium, and the list goes on. There's actually more. But this is an incomplete list. And then there are metals that are above this line that do not corrode when you throw it into acid. At least most acids. So copper is one of them. Silver is another one. This is an incomplete list. Let me tell you some more. Mercury, platinum, palladium, rhodium, ruthenium. What do you know about those metals? So think about iron. So iron metal versus platinum metal. What can you tell me about platinum versus iron? Is it cheap or expensive? Expensive. You notice the noble metals, the ones that don't react, they're the ones that tend to be more expensive. And so copper, I mean, it's a relatively expensive metal. It's not the cheapest. It's not the most expensive. It's not as expensive as platinum. Platinum is more expensive than gold, but actually platinum is more common than gold. So rarity does not always mean expense. So platinum is more expensive because it's very useful. So which also tells you what metals you put into your teeth. So I have dental fillings. They're mercury amalgam fillings. And well, the reason I use mercury because it's easy to use. So mercury is a liquid, and you can take mercury, zinc, copper, and silver. You can rub it together. It's a liquid. You can rub it together. It forms this kind of soft stuff, and you stick it in your tooth, and you push down on it, and you can fill all the holes, and then you can form it, and you just like, all right, don't eat anything hard for a day or so, and now you got a hunk of metal in your teeth. Now we tend to use composites instead. But I mean, some places still use mercury amalgams. And mercury is good because it won't dissolve in acid. So you can drink your orange juice, drink your lemon juice, and that kind of thing. And your mouth tends to have an acidic pH. So if you were to put like iron teeth, like Jaws, and remember, I don't know if you've seen I forget which James Bond that was. Jaws had the iron mouth. He would have corrosion problems. So that would not be a good source of dental apparatus. So false teeth, fillings, dental work, they're always copper, silver, gold, that kind of thing, or mixtures of that, or mercury, or mixtures therein of alloys. Please. Yeah, please.
Can you go back? What's the correlation between the expensiveness of a metal and its place as a noble metal on the chart itself?
Okay, generally speaking,
what was the connection?
The connection, the expensive metals are the ones that are less reactive, generally speaking. Now that's not always true though. The most expensive metal there is weapons grade plutonium, which is actually chemically very reactive, right? But it's hard to make. Well, but what my point is that copper, silver, gold, mercury, they're expensive versus iron, aluminum, that kind of thing. Yeah. Sorry if that was not clear. Okay, but if you look here, so let me throw another thing in here. Here is nitric acid. So right where this other blue line is nitric acid. So we have plain old acid, and well, I should say acid with nitrate anions. So acid with nitrate anions, this is above silver. So silver and copper will actually dissolve in nitric acid. They won't, if you put silver or copper into hydrochloric acid, sulfuric acid, citric acid, it won't dissolve. It won't react. You throw it into nitric acid though, and it will react. So, and if you look even higher here, gold. I mean, gold is also known as not reacting at all. Really, you can get gold to react. It's really hard to get gold to react. But if you throw gold into nitric acid, nothing will happen. So, because it's, again, just like, are you ready to rumble? It's above this line. It won't react. Can you get gold to react? Yes, you can. You can do it using something called aqua regia. That is, it's 3 parts hydrochloric acid to 1 part nitric. So that's known, and all concentrated, that's known as aqua regia. Have you guys heard of that before? Never heard, have you? I don't watch this show, but have you seen Breaking Bad? Apparently used it in that one. Do you guys watch? Did you use aqua regia? I don't watch that, but did you? No. Okay. So you can dissolve gold in aqua regia. It takes a long time. I mean, gold, even with aqua regia means the water of life. Okay, it's from the alchemists. Have you heard of the alchemists before? I'm sure you have. So the alchemists, we get a lot of the element names from alchemy. It's the alchemists. They were after what's called the Philosopher's Stone, not the Sorcerer's Stone like they have in Harry Potter. It's actually the Philosopher's Stone. The Philosopher's Stone is something that would convert base metals into gold and have the elixir of life. So the elixir of life will give you immortality. So, so they had aqua regia, the water of life, that could dissolve gold, because that's like, oh, it's close to the Philosopher's Stone, kind of thing. It'll dissolve platinum too. Platinum is even less reactive than gold, but it takes a very long time. And there's a story about some Jewish Nobel laureates, because when you get a Nobel Prize, it's a gold medal. Among other things, you get a plaque, you get some money, and you get a gold medal. Now it's gold plated, but it used to be pure gold. But a lot of the scientists that got the Nobel Prize were Jewish, and they didn't want the gold to fall in Nazi hands. So what they did is they dissolved all their metals in aqua regia, and then they reclaimed it later. But like I said, it takes a while. I mean, like if you had a beaker of it and you stuck your metal in, it might take a day or two to dissolve the whole thing. It's a very, very long process. And we're not going to do that demo because it costs a lot of money. Gold's not cheap. What did we learn in chemistry class today? Gold's expensive. Okay. So, which of the metals dissolve in nitric and not hydrochloric? It's silver. So, of course, I told you as an incomplete list. Mercury will too. So, don't put nitric acid in your mouth. You'll dissolve your fillings. Of course, that would dissolve your teeth too before that. Okay. So how are we doing some of our questions? All right, so let's do a problem here. So I told you some of the stuff before. The Gibbs free energy change is minus N F E0 cell. N is the moles of electrons transferred. F is Faraday's constant. So let's look at this. Use of tabulated cell potentials to calculate Gibbs free energy change for this reaction. Iodine solid plus 2 bromides makes iodide and bromine. So to save you the suspense, these are the electric cell potentials. Iodine reduction potential is 0.54. Bromine reduction potential is 1.09. So in this equation here, so remember when we balanced the oxidation reduction equations last class, and we had the lowest common denominator for the half cells. If it was 2 and 3, it was 6, that kind of thing. That's your N. N is the lowest common denominator. That's the number of moles of electrons transferred. In this case, it's easy. It's 2. They both, one's giving 2, one's gaining 2. Okay, so we have to look to the equation here. So iodine is being reduced. So I2 goes to I minus. We keep iodine as is. Bromine goes from Br minus to Br2. It's going the other way. Br minus to Br2. It's going the other way. We have to put a minus sign in front of this. So the standard cell potential here, it's going to be 0.54 plus a minus 1.09. So, okay, so this is going to be, so this is minus 0.55. I'm just doing that in my head. Right, so 1.09 minus 0.54 is minus 0.55 volts. That's the standard cell potential for this. And number of moles electrons transferred is N. This case, this is 2. And the delta G0 is that. So let's fill this in. The delta G is minus 2 moles of electrons. Faraday's constant, 96,485 coulombs per mole electron. So, right, that's Faraday's constant. And then the E0 cell is minus 0.55 volts. A volt is a joule per coulomb. So if you look at the units, the moles of electrons transfer and the coulombs cancel. So we're left, the unit-wise, we're left with joules. So minus and minus is a plus. And let me do my calculator. 2 times Faraday's constant, 96,485, times 0.55. And we get, this is then positive 106,133 joules, or, let me see, we have 106 kilojoules per mole. Well, per reaction, I should say. Kilojoules per mole reaction. I normally wouldn't put this calculation, but I'll show you that I can do this for a visitor. I can take pictures of my calculator and put it on here and give it to my students later so they can look and see what I've done so they can review it later. So, okay. So, recap with this one. We're given an equation, and we have the standard cell potentials. Okay, so we look at the equation, we determine iodine is being reduced, bromine is being oxidized. So that means we keep this reduction as is. We do the opposite of this for that. So then we can calculate the standard cell potential using that. And then using the relationships of delta G is minus NF E0 cell. We've calculated E0 cell. F is a constant. N is the number of moles of electrons transferred. In this case, it's 2. We throw in the equation, and we get 106 kilojoules. So does anybody have any questions with this? All right, here you go. Can you solve this one? Same thing. How about bromine plus 2 iodides makes, wait a second. These are positive. Bromine plus 2 iodides makes 2 bromides and iodine. So there are the cell potentials. There's Faraday's constant. There's the equation. So. Is anyone getting stuck? Everyone seems to be calculating, so that's a good thing. Is anyone questions? All right, so how many people think A, 1.1 times 10 to the 5 joules? How many think B? How many think C? How many think D? Okay, so 2 people going for C and no more answers. I'm going to come around, see where you guys are at. Okay. Okay. So, in this equation, bromine is iodine is going the other way. So, bromine is absorbing 2 electrons and iodine is, so it's 2 and 2, so N is 2 and 2. So you, so reduced to iodine is going the other way, so it's also
Oh, I got it backwards. And then when you have it together, it's the energy of the sun, but it's going to like
You got it. Did? But you actually is positive.
Yeah.
So you can make it.
Oh, so that means
You add these?
yeah.
Yeah, to get this?
For instance, this one would be,
This is being oxidized. This is positive. That's going to be because these are reduction potentials. These are adding electrons. So one of your
put it into this negative
yeah, that means oxidative. Right. These are reduction potentials. So you're gonna go the other way.
and you make
So the other way is
these are sick thing.
You got it, okay.
Just to make sure though, what was the definition for oxidization? Is that
Oxidation is losing electrons. Reduction is gaining electrons.
okay? Because I had them switched out.
Yeah. And if you forget, it says reduction potentials, and they're all adding electrons.
Hmm.
So if you look at the chart, it says reduction, and they're all being adding electrons.
Yeah, that's fine.
Okay. Going around and seeing what you voted on. Answer C. And I'm surprised no one picked up on this. It was just the opposite of the problem we just did.
Yeah, I just wanted to practice.
I guess wanted to try. Oh, so you did pick that up. Okay. You could have been extra sneaky and just gone right to the answer. Oh well, but I'm glad you did the work. But cheers to you for seeing that. Okay. So, changing topics a little bit. So remember from the last chapter, That was one of the last equations we covered. Was delta G is equal to minus RT natural log of K, K being the equilibrium constant. Okay, and delta G also equals minus NFE0 cell. So you can set these equal to each other. So minus NFE0 cell equals minus RT-lnK, and you can divide both sides by minus NF, and you can get equal to the E0 cell is equal to RT over NF. R is gas law constant 8.314 joules per mole Kelvin. T is temperature in Kelvin. N is moles of electrons transferred. F is Faraday's constant, 96,045 coulombs per mole electron. Natural log of equilibrium constant. And if you want to do it at 25 degrees Celsius, so this is a common formula. So if anyone ever takes, they use these formulas quite a bit in like aeronautic classes. So for boats and corrosion, they'll teach these classes for that. So I've had students that have come from the Navy or from just even recreational aeronautics, and they'll say, "Oh, we've seen this before." So I think we're a little spoiled now because we all have calculators. So I mean, although I'm using my smartphone, I mean the calculator, like if I want to know the sine of 12 degrees, I can just type in sine of 12 degrees, right, in this. Back before calculators and graphing calculators, you used to have books. And like I think the stereotype for nerds always carrying books probably came from the fact that the way that we used to do calculations, there was ways you can do it with using slide rules for an estimate, and you can use like for exponents. I mean, of course, you just put in your calculator now. The way that you used to do it is you would do the natural log of both sides and then multiply it out, and then look up the inverse logs in tables, either natural logs or log base 10. But I mean, if you had a book full of natural logs and a book full of log base 10, like log 10 books, that's twice as many books to carry. So what you could do then instead is use a change of base formula, and the natural log of 10 is 2.303. So that's one way. If you ever instead of taking the log and the natural log, so if you need to take the log and you take the natural log instead, if you multiply your answer by 2.303, you'll get the log base 10 answer. Or vice versa, if you have the log base 10, you want the natural log divided by 2.303. So anyways, so 25 degrees Celsius, which is 298 Kelvin, and then Faraday's constant, so using 298 Kelvin for temperature, Faraday's constant, R 8.314, and then converting to log base 10, you can convert this formula to this one here. E0 cell is 0.592 volts over N, number of moles of electrons, times the log base 10 of the equilibrium constant. And another equation. So delta G is delta G0 plus RT ln Q. You remember that from last chapter too. So the substituting them here, so the delta G is minus NFE cell. The standard, so the 0 degree means standard, so the standard Gibbs free energy plus the RT ln Q, that stays the same. You can divide out both sides by minus NF, and then include the 25 degrees Celsius and Faraday's constant. You get this equation here. And this is known as the Nernst equation. It's a relatively famous equation, mostly for, and I said for shipbuilders, it's important for corrosion. because we'll learn later about electrochemical potential and corrosion. And this equation will tell you if something is, if it's, of course, if E0 cell is positive, it means corrosion is going to happen. Now, the limit for this, though, is it doesn't tell you how fast. So corrosion can happen, but can happen slowly. And so, for instance, has anyone ever seen an aluminum boat in the ocean before? So, there are some, but generally speaking, aluminum will corrode in the presence of salt water. So you can have them, but they will do it very slowly. It's actually so aluminum. We'll learn later about corrosion. So aluminum actually. Oh, this is a. Is this aluminum? No, it's. I guess it is, but it's dyed. It's anodized. So this here is anodized aluminum. If you look at a piece of aluminum foil, have you ever noticed that there's just white lines on it? What that is, that's aluminum oxide, also known as sapphire. So aluminum creates a coating of aluminum oxide, at least in Earth's atmosphere, because there's oxygen. And so that's rust. That's aluminum rust. But iron rust, iron oxide is really flaky, and it's really soft. So aluminum oxide sapphire is really hard. So have you heard of the Mohs hardness scale before? Diamond's number 1, talc's number 10, or I'm sorry, diamond's the hardest, and I don't know which one, 1 or 10. But diamond's the hardest, and talc is, I think it's diamond's 10 is talc is 1. Sapphire, or also known as carborundum, it's number 9. It's the second hardest natural mineral on Earth. So diamond being the hardest. So aluminum oxide is really tough. So which means, so aluminum is actually a fairly reactive metal. So if you look at the chart, oops, I'm on the wrong page, sorry. If you look at, wrong one. If you look at the cell potentials, aluminum is near the bottom, which means it's very reactive. Lithium is at the very bottom, that means it's the most reactive. But aluminum is pretty far down. Aluminum is more reactive than manganese and a lot of things. So aluminum is a reactive metal, but you don't think of it as a reactive metal. Why? Because that's got a coating of sapphire around it, at least in the oxygen, at least in an oxygen atmosphere. So, but it turns out that the chloride anion will penetrate through that passivated layer, and that's what makes aluminum rust in salt water. And the other place that you can't use aluminum for is in fixtures, at least in your home, because we chlorinate the water. So if it was straight spring water with no chloride in it, it would work fine. But typically we use copper metal for water. So that's one of the reasons we don't use depending on the metal we use it for various things. One of the cautions is corrosion. And I like to tease my brother. I think I told you this story. My brother's wedding ring, it's gold with platinum on it. And I tease him like, hey, you know that platinum on there is going to corrode the gold. He's like, well, how long does that take? Hundreds of years? He's like, it's fine. So even though that there is a cell potential exists, it doesn't mean it's going to happen quickly. So, but that's the limit of thermodynamics. We don't know how fast. Okay, so let's use some of these equations. So E0 cell in K. So use the cell potentials to calculate K for the oxidation of copper. Okay, so this is easy. So 2H plus 2 electrons to make hydrogen gas. This has got 0 volts. That's an easy one. So then we have to look up the reduction potential. I guess I accidentally erased that. I normally have it on there, but let me look it up. go. Okay, copper. So the potential for copper plus 2 electrons going to copper. This is 0.34. Okay, so our E0 cell so hydrogen is going exactly as written. Copper, though, is going the other way, right? So it's going copper to copper plus 2, not this way. So that means our E0 cell, this is going to be 0 for the hydrogen plus a minus 0.34 for the copper is minus 0.34 volts. Okay? Does everybody understand how I got the E0 cell? So then we have the E0 cell, and we have this equation here, and wants to know the equilibrium constant to calculate K. So, we have to do the moles of electron. What is our N? How many moles of electrons are we transferring in this chemical reaction? 2. Yeah. N equals 2. So that means, so we got to solve for K. So N times E0 all over 0.0592 equals log base 10 of K. And you can get rid of that by taking 10 to both sides. So that means 10 to the N E0 over 0.0592 equals K. Okay? So then that means 2 moles of electrons. What is E0 cells? 0.34. 2 to the minus 0.34 over 0.0592. And put that in a calculator. Oh, 10. I'm sorry, 10 to that. So 10 to the quantity 2 times 0.34 divided by 0.0592. In doing so, we get equals 3.26 times 10 to the minus 12. Okay, so 3.26 times 10 to the minus 12. Does that mean that this is a reaction that happens a lot? Does that mean that this is a chemical reaction that shifts very far to the right, or does it shift very far to the left? So what does a really small K mean? Does that mean reactants favored or products favored? So what is K? K is products over reactants. So if K is small, does that mean that the top number is big, or does it mean the top number is small? Small. So that means that this reaction doesn't go very far. Does it happen? Yes, it does, in a really small amount. So if you throw copper into acid, you're really going, oh, you just contradicted yourself. You said that copper doesn't dissolve in acid. It really doesn't. What this is saying, 3.26 times 10 to the minus 12, that's saying that it really doesn't happen that much. It doesn't shift very far. There is still but also remember, it's an equilibrium. It's an equilibrium, which also means even though copper is dissolving, that also means copper is then redepositing. Okay, so that means that the reaction does go both ways. You're like, oh, this reaction doesn't happen. But it goes for it a little bit, but when it'll reach equilibrium very quickly, and then it'll just exchange atoms really, really superficially. So if you want, though, you can use the other equation,
this, wrong one up there. Okay, so the E0 cell is RT over NF ln K. You can also use the E0 is RT over, what's wrong, NF natural log K. This equation will work just as well. So I mean, it seems like my students prefer to use this one. I've noticed that my students like that one better than this one. You can use this one. Then in doing so, it would be the same idea. You could do E0 times NF over RT is equal to the natural log of K. And then you could take e to both sides to get rid of that. So that is an equally good, proper way to do it. It's actually more proper because you're using the natural log instead of the log. And so you have less error doing that way. But you can use this way as well. I can even show you. It'll give you, well, the answer is going to be slightly different because of the 2.303. Because the 2.303, that's going to truncate you get a truncation error from that. So e to the quantity to okay. So let me show you this. So if you look at these two numbers here. So this one is using the log base 10, and you get 3.26 to the minus 12. Using the e to that, you get 3.1567 to the minus 12. So you're like, well, what's the difference between these two? Within 2 sig figs, well, I guess, no, even 2 sig figs, this would be 3.3 and this would be 3.2. There's a little bit of error when you use the log base 10. There's a little bit of an error in that calculation, and that's from, I mean, they're close, right? You can see that they're close. The little bit of an error is in this step here. It's when you have the natural log of K is 2.303. So that skews a little bit and causes what's called a truncation error, because you truncate that term. Okay, so all right, so well, let me do a recap with this one. So you have two ways to solve this problem. You can use this equation, or you can use this equation. So we have copper reacting an acid if we're in copper iron and hydrogen gas. And we look at the cell potentials. This is the reduction potentials. Hydrogen 0, copper reduction potential is plus 0.34 volts. And that means our E0 cell, so hydrogen is being reduced. Copper is being oxidized, so we have to do the opposite of this, to the minus 0.34. Our standard cell potential is minus 0.34. Our E0, our N, number of moles electrons transferred, is 2. Rearranging the equation, we can solve for K, and we get 3.26 times 10 to the minus 12. And if you do using the other equation without all the added parts in, and putting in the numbers all properly, you get an answer close to that, but not exact, and that's due to the truncation error. That was just the truncation. That's just an illustration. That's just me showing stuff. Does anybody have any questions with this? No. Okay, so we got 1 minute class left, and I think I'll stop recording the lecture then, and I will problem session after this if you want to come.